Beyond the flat map of planets, the solar system is not empty. Above and below its familiar plane, there are hidden clouds of ice, tilted worlds, invisible boundaries, ancient dust, and magnetic regions shaped by the sun itself. Some of them may never be seen directly, yet their gravity and traces reveal that our solar system is far stranger than it appears. Stay with this quiet journey into the hidden layers above and below our cosmic home. If this story brings a moment of calm curiosity, please like the video, subscribe to the channel, and let the journey begin. Far beyond the familiar paths of planets, comets, and the sun's own flowing particles, the solar system belongs to a larger structure that is much older and much wider than any single star. It moves inside the Milky Way, a broad spiral galaxy whose thin, bright disk contains most of its visible stars, gas and dust. Above and below that disk, the galaxy does not end sharply. It fades into a vast outer halo, a dim region that surrounds the bright galactic plane like a very wide, nearly invisible envelope. The solar system is not near the edge of this halo, it lies inside the galactic disk, but the halo forms the outermost setting of its cosmic environment. To understand the strange things hidden above and below the solar system, the view begins at this largest surrounding layer where the galaxy becomes faint, old, and difficult to measure. The galactic halo contains material that is spread thinly across enormous distances. Much of it cannot be seen with ordinary light. Some of it appears through the motion of stars, through the pull felt by gas clouds, and through the way the galaxy holds together as it turns. The most important hidden mass is called dark matter, meaning matter that has gravity but does not emit or absorb light in any known ordinary way. Observations indicate that dark matter makes up most of the Milky Way's mass. Its nature remains uncertain, but its presence is inferred from the speed of stars and gas across the galaxy. Without this unseen mass, the outer parts of the Milky Way would not move as they do. In this sense, the solar system travels within a galaxy whose largest structure is shaped by something not directly visible. The halo also contains ancient stars. These stars are usually old and poor in heavy elements compared with stars in the galactic disk. Heavy elements are elements heavier than hydrogen and helium, made over time inside stars and during stellar deaths. Stars in the halo often formed early in the history of the galaxy, before many generations of stars had enriched space with heavier material. Their motions are different from the orderly rotation of many disk stars. Some move on stretched or tilted paths, carrying signs of earlier events when smaller galaxies were drawn into the Milky Way. In the quiet dark above and below the galactic disk, these old stars trace the memory of a long assembly process. Some of the strangest structures in the halo are stellar streams. A stellar stream is a long ribbon of stars that once belonged to a smaller galaxy or a star cluster, later stretched apart by the Milky Way's gravity. These streams can arc across the sky, faint and difficult to detect because their stars are spread thinly over great distances. They show that the halo is not a smooth, empty shell. It is layered with remains of past encounters. The Milky Way has grown by pulling in smaller systems, and their fragments remain as trails above and below the disk. The solar system does not pass through these streams in any ordinary daily sense, but it exists inside a galaxy whose outer regions still carry the marks of older collisions. Gas also occupies the halo, though it is far thinner than the air of any planet and far thinner than many clouds inside the galactic disk. This gas can be extremely hot, with temperatures reaching millions of degrees Celsius, not because it is dense like a flame, but because its particles move very fast. It is so thin that a spacecraft passing through it would not feel heat as a hand feels heat near fire. Scientists detect it through its interaction with light, especially in wavelengths beyond ordinary vision, and through signs of ionized atoms, meaning atoms that have lost electrons. Observations indicate that this hot halo gas may hold a large amount of ordinary matter, though its full distribution remains uncertain. The halo is important because it connects the Milky Way to the space between galaxies. Material can flow into the halo from outside, and material can be pushed into it from inside the galaxy by stellar winds and exploding stars. This makes the halo a kind of exchange region, where the galaxy breathes slowly over cosmic time. Gas may cool and later join the disk, where it can become part of future stars. Other gas may remain suspended for long periods, held by gravity and pressure. The process is not simple, and many details remain under study, but the halo is not a passive emptiness. It is a broad reservoir surrounding the visible galaxy. Above and below the solar system in the galactic sense, the disk of the Milky Way thins out into this halo. The words above and below here refer to the plane of the galaxy, the broad flattened region where most stars orbit. The solar system has its own tilted planes and directions, but at this scale it is only a tiny point inside the larger galactic disk. Looking away from the Milky Way's bright band means looking into regions where fewer disk stars block the view, and where distant galaxies can be seen more clearly. These high galactic latitudes open outward into the halo and beyond, making the sky seem darker and deeper. The halo also contains globular clusters, dense groups of old stars bound together by gravity. A globular cluster can contain hundreds of thousands of stars packed into a rounded form. Many orbit the Milky Way outside the main disk, above and below it, moving through the halo on wide paths. Their stars are among the oldest known in the galaxy, and they help measure the age and early development of the Milky Way. They are not hidden in the same way as dark matter, because many can be seen with telescopes, but their meaning is hidden in their ages, motions, and chemical patterns. Each cluster is a preserved record from an early stage of galactic history. At this outermost scale, the solar system is not a separate island. It is a small moving part inside a layered galaxy. The Sun follows a path around the Milky Way, accompanied by planets, moons, asteroids, dust, and distant icy bodies. Above and below its path, the great galactic halo extends as a dim and ancient environment. It contains old stars, stretched streams, hot gas, globular clusters, and an unseen mass that dominates the galaxy's gravity. Most of these things do not affect Earth in a direct daily way, yet they define the deeper setting in which the solar system exists. The strange hidden regions above and below begin not with nearby planets, but with the faint outer envelope of the galaxy itself, where light becomes sparse. Motion carries ancient memory, and gravity reveals more than vision can see. Inside the wide galactic setting, the Sun travels through a much smaller and more immediate region of space. This region is not empty. It contains a thin mixture of gas and dust that belongs to the interstellar medium, the material between stars, near the Sun. This material forms a faint, warm cloud often called the local interstellar cloud. It is difficult to picture because it is far thinner than any cloud in Earth's atmosphere. A room-sized volume of air on Earth contains an enormous number of molecules. A similar volume of this cloud contains only a few atoms, yet across astronomical distances, even such thin matter becomes important. It surrounds the solar system's outer influence and helps shape the conditions at the boundary of the Sun's reach. The local interstellar cloud is part of a broader region around the Sun known as the local bubble. The local bubble is a large cavity of unusually thin, hot gas in the Milky Way, likely shaped by past explosions of massive stars. Within that cavity, several smaller clouds of warmer material drift. The Sun is moving through one of these clouds now. Observations indicate that this cloud contains hydrogen, helium, dust grains, and traces of heavier elements. Some of the atoms are neutral, meaning they still hold their electrons. Others are ionized, meaning they have lost one or more electrons. The balance between neutral and ionized material helps reveal the cloud's temperature, density, and exposure to nearby radiation. The cloud is warm by interstellar standards, with gas temperatures of several thousand degrees Celsius. This warmth does not mean it would burn or glow like a flame. The cloud is so thin that its particles rarely collide. Temperature in this setting describes particle motion rather than everyday heat felt through dense matter. The atoms move quickly, but there are too few of them to carry much heat to a solid object. A spacecraft in such a region experiences space as cold and nearly empty. Even though instruments can measure the energetic motion of individual particles, this difference between temperature and heat is central to understanding many hidden regions above and below the solar system. The Sun does not sit still inside this cloud. It moves through the Milky Way, and the cloud itself has its own motion. The relative flow of interstellar material past the Sun can be measured through atoms that enter the outer solar system, and through the way starlight is absorbed by gas between Earth and nearby stars. Absorption means that atoms remove certain wavelengths of light, leaving patterns that reveal their presence. By comparing such patterns from many nearby stars, scientists map the direction and properties of the surrounding cloud. The result is not a sharp picture like a photograph, but a careful reconstruction from faint signs in light. Dust grains also drift within this local interstellar material. These grains are tiny solid particles made from elements such as carbon, silicon, oxygen, magnesium, and iron, combined in minerals and other compounds. They are much smaller than sand grains. Some interstellar dust enters the solar system, though much of it is filtered or redirected by magnetic fields and solar particles. Dust may seem minor, but it carries information about the life cycle of matter in the galaxy. It forms around aging stars, survives in clouds, becomes part of new stars and planets, and is later returned to space again. Near the Sun, these grains are sparse, but they are part of the quiet material stream through which the solar system moves. The local interstellar cloud has a magnetic field. A magnetic field is a region where charged particles and magnetic forces are guided or influenced. In space, magnetic fields do not need metal wires or solid magnets. They can thread through thin plasma, which is gas containing charged particles. The local interstellar magnetic field helps shape how the solar system's outer bubble meets the surrounding cloud. Its direction and strength are studied through starlight polarization, energetic particles, and spacecraft measurements. Polarization refers to the alignment of light waves after they interact with dust or magnetic fields. These measurements show that the nearby interstellar environment has structure, even though it is extremely diffuse. The cloud's composition matters because it represents the material just outside the Sun's own protective flow. Hydrogen and helium dominate, as they do across much of the universe, but heavier elements provide key details. The amount of oxygen, nitrogen, neon, magnesium, and iron helps show how interstellar matter has been processed by generations of stars. Some atoms remain in gas form, others are locked into dust grains when certain elements appear less abundant in the gas. It can indicate that they have become part of solid dust. This pattern allows scientists to infer the hidden solid content of the cloud from the light of stars beyond it. The edges of the local interstellar cloud are not known with perfect precision. Its shape may be irregular, and nearby clouds may overlap or lie close together along different lines of sight. Observations indicate that the Sun may have entered the present local cloud within the last several thousand to several tens of thousands of years, though exact timing remains uncertain. The Sun may also leave it in the future, but the boundary is not like a wall. It is a gradual change in density, temperature, ionization, and motion. At this scale, hidden structure is often measured as a shift in spectral lines, not as a visible border. Above and below the solar system, in directions away from its familiar planetary plane, the same local interstellar material continues. It does not arrange itself according to the orbits of planets. It belongs to the larger flow of gas around the Sun. The solar system's plane is a local arrangement made from the ancient disk of material that formed the planets. The local interstellar cloud surrounds that arrangement from all directions, including high above and deep below the planetary plane. Its atoms and dust grains form the nearby outer environment into which the Sun's influence presses. This cloud is strange because it is almost nothing by ordinary standards, and yet it is not nothing. It is thin enough to seem empty, but it carries gas, dust, magnetic fields, and a history of stellar change. It is gentle in density, but wide in reach. It holds traces of old stars and interacts with the Sun's outward flow. The solar system moves through it quietly, like a small bright vessel inside a vast faint mist. The hidden things above and below begin to take a closer form here, no longer as the whole galactic halo, but as the local material through which the Sun is passing at this moment in galactic time. Within the faint material around the Sun, the solar system has its own outer interaction region. This region is not marked by a solid surface, and it is not visible as a bright shell in ordinary light. It forms because the Sun constantly sends particles outward in all directions. This stream is called the solar wind, a flow of charged particles released from the Sun's hot outer atmosphere. The solar wind spreads through space, carrying part of the Sun's magnetic field with it. As it moves outward, it becomes thinner, but it does not vanish at once. It continues until it meets the pressure of the surrounding interstellar material. The region where these pressures begin to shape each other is one of the most remote and hidden parts of the solar system's environment. The word bow often suggests the curved wave in front of a moving boat, but around the solar system the picture is more careful. The Sun moves through local interstellar gas, and the surrounding gas flows past the solar system. For many years, scientists considered whether a bow shock might stand ahead of the heliosphere, the large bubble formed by the solar wind. A shock is a sharp change in speed, density, and pressure when a flow moves faster than waves can travel through that medium. More recent observations indicate that the local interstellar flow near the Sun may not create a strong classic bow shock. Instead, it may form a gentler bow wave or broad disturbed region. The exact structure remains an active area of study, because it depends on the speed of the Sun through the local cloud, the strength of the interstellar magnetic field, and the properties of the surrounding gas. The heliosphere is the Sun's protective bubble. It is shaped by the solar wind from within and by interstellar matter from without. Far from the planets, this bubble does not remain perfectly round. The pressure from the interstellar flow, together with magnetic fields, gives it an asymmetric form. The region facing the oncoming interstellar material is compressed more than the trailing region, above and below the planetary plane. The shape is influenced by both the Sun's magnetic cycle and the direction of the local interstellar magnetic field. The result is not a simple sphere centered on the Sun, but a changing boundary system with a front, sides, and a long region of disturbed flow. Before the solar wind reaches the outer boundary of the heliosphere, it slows down at a region called the termination shock. This is not the same as a bow shock outside the heliosphere. The termination shock lies inside the solar bubble, where the solar wind drops from supersonic speed to slower motion. Supersonic here means faster than pressure waves can travel through that plasma. At this boundary, the solar wind becomes hotter, more compressed, and more turbulent. The termination shock was crossed directly by the Voyager spacecraft, providing rare measurements from a region far beyond the planets. These measurements show that the distant solar wind does not fade smoothly. It changes in stages as it approaches interstellar space. Beyond the termination shock lies the heliosheath. This is a thick outer layer of slowed, heated solar wind. It is a region of turbulence, magnetic variation, and particle mixing. The heliosheath is still dominated by solar material, but it is already strongly affected by pressure from outside. Energetic particles move through it, some from the Sun, some from beyond the solar system, and some accelerated within boundary regions. In this layer, the solar wind is no longer a steady outward stream. It is redirected and compressed as it searches for a path around the pressure of interstellar matter. This makes the heliosheath a hidden transition zone rather than a simple edge. The interaction region above and below the solar system is especially difficult to map because no spacecraft has flown far in these directions. Most planetary spacecraft travel near the plane where the planets orbit. The Voyager spacecraft move outward on paths tilted from that plane, but they still provide only 2 direct tracks through an enormous 3-dimensional structure. Much of the shape is inferred from remote observations and models. Instruments near Earth detect energetic neutral atoms, which are atoms formed when charged particles exchange electrons and then travel in straight paths unaffected by magnetic fields. These atoms can carry information from the outer heliosphere back toward the inner solar system. By mapping them, scientists build a broad image of the distant boundary. One important discovery from such mapping is a bright ribbon of energetic neutral atoms across the sky. This ribbon is linked to the interaction between the heliosphere and the local interstellar magnetic field. Its exact cause has been studied in several models, but observations show that the outer solar boundary is influenced by magnetic structure outside the Sun's own domain. The ribbon is not a physical band of solid material. It is a pattern in particle signals, revealing where certain interactions are stronger. It shows that the hidden space above and below the planetary plane contains shaped flows and field lines, not emptiness. The pressure balance in this region involves several components. The solar wind has dynamic pressure from its outward motion. It also carries magnetic pressure from the Sun's magnetic field. The interstellar medium has gas pressure, magnetic pressure, and pressure from cosmic rays, which are high-energy particles moving through the galaxy. None of these pressures is large by everyday standards, but across vast distances they determine the shape of the heliosphere. A slight difference in pressure can shift boundaries by many astronomical units. An astronomical unit is the average distance between Earth and the Sun. In this distant region, even such a large distance becomes a measuring step rather than a final scale. The solar wind itself changes over time. The Sun has an activity cycle of about 11 years, during which its magnetic field, sunspots, eruptions, and wind patterns vary. These changes travel outward, reaching the distant heliosphere long after they leave the Sun. The outer interaction region therefore carries a delayed record of solar activity. It does not respond instantly. A change near the Sun moves outward through the solar wind and reaches the boundary years later. At the same time, the outside interstellar conditions remain present, pressing inward. The region becomes a slow meeting place between changing solar output and steadier galactic surroundings. This outer bow region is strange because it is both part of the solar system and part of interstellar space. It has no ground, no sky, and no visible surface, yet it has structure. It is made from pressure, fields, particles, and motion, above and below the planets. It curves and shifts according to forces that are almost too thin to imagine. The solar system moves inside a faint local cloud, and the sun's wind pushes back against that cloud, where these two flows meet. The hidden architecture of the solar system begins to appear, not as walls or rings, but as a quiet boundary shaped by pressure against pressure. Inside the outer interaction region, there is a boundary that marks the end of the sun's dominant particle flow. This boundary is called the heliopause. It is not a hard surface, and it is not a shell that could be touched like ice or stone. It is the place where the outward pressure of the solar wind is balanced by the pressure of interstellar material. On one side, particles and magnetic fields mainly belong to the sun. On the other side, particles and magnetic fields mainly belong to the surrounding space between stars. The heliopause is therefore a border made from motion and pressure rather than solid matter. It is one of the most important hidden boundaries above and below the solar system, because it separates the sun's inner domain from the wider galactic environment. The word heliopause comes from the sun's name in Greek and the idea of a pause or stopping place. What pauses there is not the sun's light, because sunlight continues far beyond it. What changes is the solar wind. The solar wind begins near the sun as a fast stream of charged particles, mostly protons and electrons, and it expands outward across the planetary system. By the time it reaches the outer heliosphere, it has already slowed and heated in the heliosheath. At the heliopause, the flow no longer pushes freely outward. It is turned, mixed, and held back by interstellar pressure. The sun continues to shine across the boundary, but the sun's moving plasma no longer controls the space beyond in the same way. The heliopause was measured directly by Voyager 1 and Voyager 2. These spacecraft were launched in the late 1970s and travelled past the giant planets before continuing outward. Voyager 1 crossed the heliopause in the year 2012. Voyager 2 crossed it in the year 2018. Their crossings did not happen at the same distance from the Sun, because they moved in different directions and encountered different parts of an uneven boundary. The measurements showed a sharp increase in galactic cosmic rays, a drop in particles from the Sun, and changes in plasma conditions. These changes confirmed that each spacecraft had entered interstellar space, though they remained deeply within the Sun's gravitational influence. The heliopause is sometimes misunderstood as the edge of the solar system. It is better described as the edge of the heliosphere, the Sun's plasma bubble. The solar system, if defined by objects that orbit the Sun, extends much farther because distant, icy bodies remain gravitationally bound well beyond the heliopause. The heliopause marks a change in the space environment rather than the end of all solar membership. Above and below the planetary plane, this distinction matters. A spacecraft can pass beyond the solar wind's bubble and still move through a region where the sun's gravity guides remote icy objects. The heliopause is a boundary of particles, not a boundary of ownership. The shape of the heliopause is influenced by the local interstellar magnetic field. A magnetic field can guide charged particles and resist motion across field lines. Because both the solar wind and the surrounding interstellar medium contain charged particles, magnetic pressure becomes important. The heliopause may be stretched, folded, or uneven where magnetic fields drape around it. Draping means that field lines bend around an obstacle, much as flowing water curves around a stone, though the physical process is magnetic rather than watery. This draped field can affect how particles enter or leave the heliosphere. It also makes the boundary different in different directions. The heliopause has no single fixed distance. Its position changes with solar activity and interstellar pressure. When the solar wind is stronger, the boundary can be pushed outward. When solar pressure weakens, the boundary can move inward. These changes occur over long times because the solar wind takes years to travel from the inner solar system to the outer boundary. The heliopause therefore carries a delayed imprint of the Sun's past activity. It is not a still wall. It breathes slowly, expanding and contracting as the Sun changes. The motion is small compared with the scale of space, but it is real enough to alter conditions across many millions of kilometers. Cosmic rays help reveal the importance of the heliopause. Cosmic rays are high-energy particles, mostly atomic nuclei, that travel through the galaxy at great speed. Many come from violent events such as supernova remnants, though their full range of sources remains under study. The heliosphere partly shields the inner solar system from lower-energy galactic cosmic rays. It does not block them completely, but the solar wind and magnetic fields reduce and scatter some of them. At the heliopause, the balance changes. Voyager measurements showed that cosmic rays from the galaxy become more common beyond the boundary, while particles linked to the Sun decrease. This shift shows that the heliopause acts as a filter, not as an absolute barrier. The boundary also contains energetic neutral atoms. These are atoms without charge that form when charged particles exchange electrons. Once neutral, they are less affected by magnetic fields and can travel long distances in straight paths. Some energetic neutral atoms created near the heliopause or heliosheath move inward, where spacecraft near Earth can detect them. This allows scientists to study the outer boundary without sending instruments to every direction. The resulting maps show that the heliopause is not smooth in every place. It has regions where particle signals are stronger, and these patterns reflect the structure of the surrounding magnetic field and plasma. Above and below the solar system, the heliopause encloses the planetary region like a broad, uneven bubble. The planets orbit in a relatively flat plane, but the heliopause extends around them in 3 dimensions. Its northern and southern forms are not fully known from direct measurement. Most knowledge comes from limited spacecraft paths, particle maps, and computer models based on physics. Observations indicate that the heliosphere may be more compact and rounded than older long-tail pictures suggested. Though its exact form remains uncertain, the uncertainty is not a failure of science. It reflects the difficulty of studying a boundary that is extremely far away, very thin, and constantly changing. The heliopause is strange because it is both definite and gradual. It can be crossed, and spacecraft can measure clear changes, yet it is not a visible line drawn through space. Around it, particles mix, fields bend, and pressures adjust. The Sun's plasma ends its dominance there, but the Sun's light and gravity continue. The boundary belongs to a realm where familiar ideas of inside and outside become more precise and less ordinary. It is the edge of a moving bubble around a star, shaped by the quiet push of interstellar matter. In this region, above and below the planetary paths, the hidden architecture of the solar system becomes a subtle meeting of 2 environments, one carried outward by the Sun and one waiting in the dark between stars. Far beyond the heliopause, the Sun's wind no longer dominates the surrounding space, but the Sun's gravity continues outward for a much greater distance. In this remote gravitational region lies the outer Oort cloud, a vast and uncertain shell of icy bodies thought to surround the solar system in all directions. It has not been observed directly as a complete structure. Its presence is inferred from the paths of long-period comets, which arrive from distant regions on highly stretched orbits. These comets can approach the inner solar system from many directions, not only from the flat plane where the planets move. Their wide range of inclinations suggests a distant reservoir shaped more like a sphere than a disk. Above and below the planetary plane, this hidden cloud may extend into deep darkness, holding icy remnants from the solar system's earliest time. The outer Oort cloud is not a cloud in the ordinary sense. It is not a mist, and it is not continuous. It is thought to contain many separate icy bodies, each moving along a long, slow orbit around the Sun. The distances involved are so great that ordinary scales lose their familiar meaning. Some estimates place the outer part of the Oort cloud tens of thousands of astronomical units from the Sun, perhaps reaching close to the limit where passing stars and the gravity of the Milky Way can disturb solar orbits. An astronomical unit is the average distance between Earth and the Sun. In the outer Oort cloud, that distance becomes only a small step in a much wider gravitational field. The bodies of the outer Oort cloud are likely made from ice, dust, rock, and frozen gases. They may include water ice, carbon dioxide ice, carbon monoxide ice, methane ice, and ammonia-bearing materials. Their surfaces are expected to be dark and cold, altered by long exposure to cosmic rays and faint starlight. At such distances, sunlight is extremely weak. The Sun would appear as a bright star rather than a warming disk. Temperatures are low enough for many volatile substances to remain frozen for billions of years. Volatile substances are materials that can easily become gas when warmed, and in the outer Oort cloud they stay locked in ice unless an object is disturbed inward. The origin of the Oort cloud is tied to the early solar system. The Sun and planets formed from a rotating disk of gas and dust. In the young planetary system, icy bodies formed beyond the warmer inner regions, especially near and beyond the giant planets. Gravitational encounters with Jupiter, Saturn, Uranus, and Neptune likely scattered many of these bodies outward. Some were ejected from the solar system completely. Others were sent onto very wide orbits that passing stars and the galactic tide could later reshape. The galactic tide is the gentle gravitational influence of the Milky Way across the solar system. Over long times, it can lift and alter distant orbits, making them less tied to the original planetary plane. This explains why the outer Oort cloud may surround the Sun in a broad spherical form. Objects scattered outward by planets first begin with paths related to the planet-forming disk, but distant gravitational nudges gradually change their directions. Passing stars, molecular clouds, and the overall pull of the galaxy can raise or lower their orbital inclinations. Inclination means the tilt of an orbit relative to a reference plane. In the outer Oort cloud, inclinations may become widely distributed, so bodies can move above, below, and across the planetary plane from nearly any direction. This makes the region one of the most important hidden structures for understanding what lies beyond the flat solar system. Long-period comets are the main evidence for this distant reservoir. These comets take more than 200 years to orbit the Sun, and many take far longer. Some may require thousands, millions, or even longer spans to complete one path. When one is disturbed inward, it begins to fall toward the Sun along a long arc. As it reaches warmer regions, its ices turn into gas and carry dust outward, forming a coma and sometimes a tail. The bright comet seen from Earth is only the active stage of an object that may have spent most of its life frozen in the far dark. The direction from which such comets arrive helps reveal the hidden shape of their source. The outer Oort cloud is weakly bound. The Sun's gravity still reaches it, but only gently. A passing star does not need to come very close by planetary standards to disturb objects there. Even a small gravitational tug, acting on a body with a slow and distant orbit, can change its path enough to send it inward or outward. The Milky Way's tide also works over long spans, raising and lowering the closest approach points of distant comet orbits. These effects do not act like sudden explosions. They're quiet, slow adjustments. Over millions and billions of years, they keep the outer Oort cloud active as a source of occasional comets. The outer cloud also marks a place where the solar system becomes difficult to define. The heliopause is much closer, but it is only the boundary of the sun's wind. The Oort cloud lies far beyond it, in space already filled with interstellar material. Its objects still orbit the sun, but they move in a region where galactic gravity and nearby stars have increasing influence. This makes the outer Oort cloud a transitional gravitational zone. It belongs to the solar system by orbit, but it is shaped by the galaxy around it, above and below the planets. The sun's distant hold becomes wide, faint, and easily disturbed. No telescope has yet mapped the outer Oort cloud object by object. The bodies are expected to be too small, too cold, and too faint at their great distances. Their existence is therefore understood through indirect evidence, especially comet orbits and dynamical models. Observations indicate that a distant comet reservoir is needed to explain the supply of long-period comets. Details such as its total population, exact outer edge, and mass remain uncertain. Some models suggest a large number of icy bodies. Others differ in how the cloud formed and how many objects survived. The uncertainty is stated carefully because the region is hidden by distance rather than by mystery alone. The strange nature of the outer Oort cloud lies in its quiet scale. It is not bright, dense, or near, yet it may contain a vast population of ancient icy bodies. It surrounds the solar system from above, below, and all around, far beyond the planets and beyond the sun's particle shield. It preserves material from early solar history while also responding to the Milky Way. Its objects move slowly in darkness, waiting under weak sunlight and gentle gravity. Only a few are disturbed inward, becoming visible as comets for a short part of their existence. In this distant shell, the solar system is no longer a flat arrangement of planets, but a faint sphere of hidden ice held loosely around a star. Within the far outer shell of distant comets, the solar system may hold a somewhat closer reservoir of icy bodies. This region is often called the inner Oort cloud, though its exact form and population remain uncertain. It lies much farther away than the known belt of icy worlds beyond Neptune. Yet closer than the most distant part of the Oort cloud, it is still beyond direct detailed observation, and it is studied mainly through the unusual orbits of objects that travel far from the sun without fully leaving its gravity. The region is hidden not because it is blocked from view, but because its bodies are small, dark, cold, and very far away. They reflect so little sunlight that even large telescopes can find only the nearest and brightest examples. The inner Oort cloud is sometimes described as a bridge between the scattered outer solar system and the spherical outer Oort cloud. Its bodies may have orbits that are stretched and remote, but not as easily changed by passing stars as the farthest Oort cloud objects. The sun holds them more strongly than it holds the outermost comet reservoir. Because of this stronger hold, they may preserve older patterns from the early scattering of icy material by the giant planets. At the same time, they can still be influenced over long periods by galactic tides and rare stellar passages. Their paths may be tilted far above or below the planetary plane. making this region another hidden structure that does not fit the simple, flat picture of the solar system. One reason scientists consider such a region is the existence of distant bodies with unusual orbits. Some known objects move far beyond Neptune and never come close enough to be strongly scattered by it today. Their closest points to the Sun are too distant for ordinary encounters with Neptune to explain their present paths easily. These objects are sometimes called detached objects, meaning their orbits are separated from strong direct control by Neptune. Sedna is one example often discussed in this context. It travels on a very elongated path, with the closest approach still far beyond Neptune and a farthest reach much deeper into the outer solar system. Its orbit suggests that some influence in the past lifted it away from the region of the known planets. Several possible explanations exist for such orbits, and the certainty is limited. A passing star during the Sun's early life could have disturbed distant icy bodies. The Sun may have formed in a cluster with other young stars, where close stellar passages were more common than they are now. The gravity of an unseen planet has also been proposed as one possible influence on some distant orbits, though no such planet has been confirmed. Interactions with the early planet-forming environment may also have played a role. Observations indicate that unusual distant orbits exist, but the exact cause remains uncertain. The inner Oort cloud is therefore a region where evidence is real, while interpretation stays cautious. The bodies in this region are likely remnants from the early solar system. They may contain frozen water, methane, nitrogen, carbon monoxide, and complex organic-rich material. Organic here means carbon-based chemistry, not life, at very low temperatures. Such materials can remain preserved for enormous spans of time. Surfaces may become darkened and reddened by radiation that slowly changes frozen compounds. Because the Sun is so faint at these distances, geological activity is expected to be limited for most small bodies. Some larger objects may have had internal warmth early in their histories from radioactive decay or impacts, but many are likely cold, quiet, and ancient. The inner Oort cloud differs from the outer Oort cloud in how strongly it responds to the galaxy. In the outer cloud, the Milky Way's tide and passing stars can change orbits more easily. In the inner cloud, the Sun's gravity is stronger, so those outside forces act more slowly and less efficiently. This means that objects in the inner Oort cloud may be more stable over the age of the solar system. They can remain hidden for billions of years without being sent inward often. As a result, the region may contain a large number of bodies while contributing fewer visible comets than the outer reservoir. Its silence may come from stability rather than emptiness. Above and below the planetary plane, inner Oort cloud objects may follow highly inclined paths. Some may move on orbits that rise far out of the plane before returning toward distant points closer to the Sun. These tilts are important because they show how the solar system's outer architecture becomes more three-dimensional with distance. The inner planets and most large planets move near a shared plane, but remote icy bodies can occupy a much wider volume. The solar system becomes less like a flat disk and more like a layered field of paths, with each object tracing a slow curve through darkness. The region is also important for understanding long-period comets. Some comets may come from the outer Oort cloud, where outside forces can send them inward. Others may have histories linked to closer distant reservoirs, especially if their orbits have been changed over time by planets after entering the inner system. Tracing a comet back to its exact source is difficult, because each passage near the Sun and planets can alter its path. Heat also changes the body itself, releasing gas and dust. A comet seen near Earth may be the visible end of a long hidden journey that began in a distant reservoir whose structure is still uncertain. Because direct observations are limited, Computer models play a major role in studying the inner Oort cloud. These models begin with possible early arrangements of planets and icy bodies, then calculate how gravity changes orbits over long times. They test whether known distant objects can be produced by scattering passing stars, galactic tides, or other influences. Models do not replace observation, but they help determine which histories are physically possible. Different models can produce similar outcomes, so new discoveries are needed to narrow the choices. Each additional distant object with a well-measured orbit adds a small piece to the hidden map. The inner Oort cloud is strange because it may be large, ancient, and real, yet only faintly sampled. It may hold bodies that almost never visit the inner solar system. It may preserve clues about the Sun's birth environment and the early rearrangement of planets. It may also show how the solar system changes from a flattened planetary structure into a broad remote volume. Its objects do not shine by themselves. They wait in cold orbits under weak sunlight, moving slowly through regions where years are too small a measure and where gravity records old events. In this inward step from the farthest shell, the solar system remains dark and hidden, but its shape begins to show more memory of its own beginning. Closer to the Sun than the inner Oort cloud, the solar system contains a disturbed region of icy bodies known as the scattered disk. This region lies beyond Neptune, but it is not a quiet, even belt. It is made of objects whose orbits have been stretched, tilted, and reshaped by gravitational encounters, especially with Neptune. The scattered disk belongs to the outer solar system, yet it is more directly connected to the known planets than the Oort cloud is. Its objects still carry the signs of contact with Neptune's gravity. Some travel far above or below the main planetary plane. Others move inward near Neptune's path and then outward into deep cold. In this region, the solar system begins to look less orderly, less flat, and more unsettled. The scattered disk forms through gravitational scattering. Scattering means that an object's path changes after it passes near a much more massive body. In the outer solar system, Neptune is the main planet responsible for this process. A small, icy body that comes close to Neptune can gain or lose orbital energy. Its orbit may become longer, more tilted, or more stretched. Sometimes it may be pushed into a path that reaches far from the Sun. Sometimes it may be sent inward or eventually removed from the solar system. The process does not require impact. Gravity alone changes the orbit, quietly and efficiently, across repeated encounters. The objects in the scattered disk are made mostly of ice and rock. They may contain water ice, methane ice, nitrogen ice, carbon-rich material, and silicate minerals. Silicates are rocky minerals containing silicon and oxygen. Many of these bodies are dark or reddish, because radiation changes their surface chemistry over long periods. Some are large enough to be rounded by their own gravity, while many others are irregular fragments. Their surfaces are cold, and sunlight is weak. Most do not show activity like comets while they remain far away, but some can become active if their orbits carry them closer to the Sun. The scattered disk is important because it is a source region for some short-period comets. Short-period comets complete orbits in less than 200 years. Many of them belong to the Jupiter family group, meaning their present paths are strongly influenced by Jupiter. Their deeper source, however, is often linked to icy bodies that began beyond Neptune. Over long times, gravitational steps can move an object from the scattered disk into a path that reaches the giant planets. Encounters then pass it inward from one planetary influence to another. By the time such a body becomes visible as a comet, its earlier history may be partly hidden by many orbital changes. The scattered disk is not sharply separated from the Kuiper belt, but it has a different character. The Kuiper belt includes many objects with more stable orbits in a broad region beyond Neptune. Scattered disk objects usually have more elongated and inclined paths. Elongated means stretched into an oval rather than nearly circular. Inclined means tilted relative to the main planetary plane. These tilted paths are central to the topic of what lies above and below the solar system. Some scattered disk objects rise high above the plane before descending again, tracing enormous arcs through dim space. Their motion shows that the outer solar system cannot be understood as a thin sheet alone. Eris is a well-known example linked with the scattered disk. It is a dwarf planet, meaning a body large enough to be rounded by its own gravity, but not one that has cleared its orbital region of other objects. Eris travels on a highly tilted and elongated orbit that carries it far from the Sun. Its discovery helped clarify that Pluto is part of a broader population of icy worlds, rather than a lone outer planet. Eris is not typical in every detail, but it shows the scale of bodies that can exist in this unsettled region. It also shows how distant icy worlds can remain hidden until careful surveys find their faint motion against the background stars. Scattered disk objects move slowly. At their great distances, orbital periods can last hundreds or thousands of years. A body may spend most of its orbit far from the Sun, moving through weak light, and only a smaller part closer to Neptune's region. Because they are faint, they're easiest to detect when they're near the closer parts of their orbits. This creates an observational bias. Observational bias means that the objects found by telescopes are not always a complete sample of what exists. Many scattered disk objects may remain unseen because they are too distant, too small, or too dark at the time of observation. Neptune's role gives the scattered disk a continuing restlessness. Some objects are in temporary stable arrangements, but many remain vulnerable to future changes. Their paths can be altered again when they come near Neptune, or through resonances with Neptune's orbit. A resonance occurs when two orbital periods form a regular ratio, allowing repeated gravitational tugs to build up over time. In some cases, resonances can protect objects from close encounters. In other cases, they can increase instability. The same planet can create both order and disorder, depending on the exact path of the small body. Above and below the planetary plane, the scattered disk adds a broad vertical thickness to the outer solar system. It is not spherical like the outer Oort cloud may be, but it is much thicker than the calm image of planets moving in a flat arrangement. Objects with high inclinations can occupy regions far from the path of Neptune, even while their orbits remain connected to Neptune's gravitational history. This makes the scattered disk a transition between the flatter world of the planet-forming disk and the more three-dimensional reservoirs farther out. It is closer, more active, and more strongly shaped by known planetary gravity. The scattered disk also preserves signs of migration in the early solar system. Planetary migration means that planets change their distances from the Sun after they formed, due to gravitational interactions with leftover small bodies and with each other. Evidence suggests that Neptune did not always occupy its present orbit. As it moved outward, it could have scattered icy objects, trapped some in resonances, and left others on unstable paths. The scattered disk therefore holds clues to a time when the outer planets and icy debris were still rearranging. It is not only a present region of disturbed orbits, but also a record of early motion. This region is strange because it is both a reservoir and a pathway. It stores icy bodies for long times, yet it also sends some of them inward. It appears sparse, but its objects may be numerous. It lies beyond Neptune, but Neptune still shapes it. Its bodies can travel high above and far below the planetary plane, making the solar system wider in form than the visible planets suggest. In the scattered disk, hidden ice does not rest in perfect calm. It follows disturbed paths through cold space, carrying ancient material along orbits that gravity has stretched into long, tilted curves. Inside the disturbed scattered disk lies a more structured region of icy bodies known as the Kuiper Belt. It extends beyond Neptune and contains many small worlds left from the early solar system. Unlike the distant Oort cloud, the Kuiper Belt is observed directly through telescopes. Unlike the scattered disk, many of its objects follow more stable paths. It is not a narrow ring, and it is not perfectly flat, but it keeps a clearer connection to the ancient disk of material from which the planets formed. Above and below the planetary plane, the Kuiper Belt has thickness, structure, and variation. It is a cold outer region where ancient material remains preserved in darkness, moving slowly under weak sunlight. The Kuiper Belt is made of icy and rocky bodies. Some are small fragments only a few kilometers across. Others are large enough to become rounded by their own gravity. Pluto, Haumea, Make, and other dwarf planets belong to this wider outer population. A dwarf planet is a body that orbits the Sun, is rounded by gravity, and has not cleared its orbital region. This definition places such worlds in a shared environment rather than alone. Their presence shows that the outer solar system contains many preserved remnants, not just one distant object at the edge of the planets. The belt is shaped strongly by Neptune. Some Kuiper Belt objects move in orbital resonances with Neptune, meaning their orbital periods follow repeated ratios with Neptune's period. Pluto is in such a resonance, completing 2 orbits around the Sun for every 3 orbits of Neptune. This arrangement helps prevent close encounters even though Pluto's path crosses inside Neptune's distance from the Sun for part of its orbit. Resonance can act like a quiet rhythm that protects an object from being scattered away. It can also organize groups of bodies into patterns that reveal how Neptune shaped the region over time. Other Kuiper Belt objects belong to a more stable group often called the classical belt. These objects generally have orbits that are less stretched than scattered disk objects and are not controlled by strong present-day resonances. Some classical objects have low inclinations, staying relatively near the planetary plane. Others have higher inclinations, rising farther above and below it. This division suggests a complex history. The colder, lower inclination population may preserve material closer to where it formed. The hotter, higher inclination population may have been stirred or displaced by early planetary movement. Here the words cold and hot describe orbital motion, not surface temperature. Cold orbits are calmer and less tilted. Hot orbits are more excited and more inclined. The Kuiper Belt is one of the best places to study early solar system material because many of its objects have remained cold for billions of years. Their interiors may preserve mixtures of ice, rock, and organic-rich compounds from the time of planet formation. Their surfaces, however, have been altered by sunlight, cosmic rays, and impacts. Some bodies appear reddish because radiation changes methane and other carbon-bearing ices into more complex materials. Others are more neutral in colour, suggesting different surface compositions or histories. Each faint colour and brightness measurement becomes a clue to chemistry in a region where direct sampling remains rare. New Horizons, the spacecraft that passed Pluto in the year 2015, showed that Kuiper Belt worlds can be more active and varied than once expected. Pluto has mountains of water ice, plains of nitrogen ice, hazes in its atmosphere, and signs of geological renewal. Its moon Charon has canyons and surface differences that record internal change. Later, New Horizons visited a smaller Kuiper Belt object named Arakoth. Arakoth has a gently joined double-lobed shape, suggesting a slow merger of two bodies in the early outer solar system. These observations show that the Kuiper Belt contains both complex large worlds and small preserved objects. Above and below the main plane, the Kuiper Belt's thickness comes from the inclinations of its objects. Inclination is the tilt of an orbit relative to a reference plane. A body with a low inclination stays near the broad path of the planets. A body with a high inclination climbs well above it and later drops below it during each orbit. Because these orbits are very large, even a moderate tilt can lift an object far from the plane in absolute distance. The belt therefore forms a broad, shallow volume rather than a thin painted line around the Sun. The Kuiper Belt is also a record of planetary migration. Evidence indicates that the giant planets did not remain exactly where they formed. Neptune likely moved outward through a population of icy bodies. As it migrated, it scattered some objects, trapped others in resonances, and left some in stable regions. The present Kuiper Belt is therefore not simply a leftover ring. It is a rearranged field of survivors, its gaps, resonant groups, tilted populations, and distant edges all carry traces of this early movement. The belt's structure is a fossil pattern written by gravity. The outer edge of the main Kuiper Belt appears sharper than a simple gradual fading might suggest. The number of known objects drops beyond a certain region, though more distant bodies do exist in other populations. The reason for this structure remains studied. It may reflect how material was distributed in the early solar disk, how Neptune migrated, or how other forces removed or rearranged bodies. Observations continue to improve as surveys find fainter and more distant objects. The belt is known far better than the Oort cloud, but it is still incomplete as a map. The Kuiper Belt is strange because it is both familiar and hidden. It contains named worlds, measured orbits, colours, moons, and visited surfaces. Yet most of its population remains faint, cold, and unseen. It lies beyond the last major planet, but it is not an empty edge. It is a wide region of ancient pieces, some calm, some tilted, some locked into Neptune's rhythms. Above and below the planetary plane, its objects trace slow paths through weak sunlight, preserving the memory of the early solar system in ice and rock. In this inward step, hidden space becomes more visible, but it remains quiet, distant, and deeply old. Inside the Kuiper Belt's broad outer structure, Neptune marks a powerful inner boundary of order and disturbance. It is the farthest known major planet from the Sun, and its gravity shapes a large region around its path. Neptune is not only a planet moving quietly through darkness. It is also a gravitational organizer, a body massive enough to sculpt small worlds, protect some of them in stable rhythms, and scatter others into stretched paths. Above and below the planetary plane, Neptune's influence helps explain why some icy bodies remain arranged in patterns while others travel on tilted and elongated orbits. In this region, the hidden architecture of the outer solar system becomes a record of repeated gravitational timing. Neptune orbits far from the Sun, where sunlight is weak and the planet receives only a small fraction of the warmth that reaches Earth. It is an ice giant, meaning a giant planet rich in water, ammonia, methane, and other compounds in forms shaped by high pressure, along with hydrogen and helium in its atmosphere. Its blue colour comes mainly from methane absorbing red light, though the full depth of its colour involves atmospheric properties still studied. Neptune itself belongs to the planetary plane, but its reach extends well beyond the path it follows. Small objects near and beyond its orbit can be moved by its gravity even when they never touch it. The planet's influence is strongest through encounters and resonances. A close encounter can change a small body's orbit quickly, stretching it or sending it into a new region. A resonance works more gradually. In a resonance, an object, a Neptune return to certain orbital positions in a repeating pattern. These repeated alignments can either stabilize the object or increase its orbital changes. Pluto provides a clear example of stable resonance with Neptune. Although Pluto's orbit is tilted and elongated, its timing prevents close approaches to Neptune. The two bodies are arranged so that their paths remain safe over long spans. This pattern shows how gravity can produce order without direct contact. Many objects beyond Neptune are grouped by these orbital rhythms. Some complete one orbit for every 2 orbits of Neptune. Others follow different ratios. Each group tells part of the story of Neptune's past movement. If Neptune migrated outward during the early solar system, its resonances would also have moved outward, sweeping through fields of icy bodies. Some objects could have been captured into these moving rhythms and carried into new orbits. This process offers a natural explanation for why resonant populations exist today. The present outer solar system is therefore not only arranged by where bodies formed, but also by how Neptune shifted through them. Neptune's region also includes its Trojan objects. A Trojan is a small body that shares a planet's orbit while staying near stable gravitational points ahead of or behind the planet. These points are called Lagrange regions, where the gravity of the Sun and planet allows small objects to remain in a repeating arrangement. Neptune Trojans move with the planet around the Sun, occupying positions that are stable over long times. Some of these objects have significant orbital inclinations, meaning they travel above and below the planetary plane while still sharing Neptune's general path. Their existence shows that even near a major planet's orbit, small bodies can occupy hidden tilted populations. The known Neptune Trojans are difficult to detect because they are distant and faint. Their discovery requires careful comparison of the images taken over time, looking for tiny points that shift against background stars. The objects likely represent only a small observed sample of a larger population. Their surfaces are expected to be dark and icy, similar in some ways to other distant small bodies. Their origins remain studied. Some may have been captured during Neptune's migration. Others may have settled into stable regions through early gravitational interactions. Observations indicate that Neptune's Trojan population could be important for understanding the outer solar system's early rearrangement. Neptune's moon system adds another strange feature to this region. Triton, Neptune's largest moon, moves around the planet in a retrograde orbit, meaning it travels opposite the direction of Neptune's rotation. This is unusual for a large moon, and suggests that Triton did not form in place around Neptune in the same way as many regular moons around giant planets. Evidence indicates that Triton was likely captured from the outer solar system. Its surface contains nitrogen ice, water ice, and young-looking terrains. Geyser-like plumes have been observed in Voyager images, likely driven by solar heating of surface or near-surface nitrogen ice. Triton is therefore a captured icy world, held close to Neptune, carrying outer solar system material into a planetary moon system. Triton's capture would have changed Neptune's earlier moons. A large captured object moving into orbit would disturb any smaller moons already present. Some could be ejected, destroyed, or rearranged. The present irregular moons of Neptune, many of which move on distant, tilted or eccentric paths, may record a history of capture and disruption. Eccentric means an orbit is stretched away from a circle. These moons are small and faint. but their paths reveal that Neptune's region is not limited to the planet and its rings. It includes a wide gravitational environment where captured bodies and tilted orbits remain as signs of past events. Neptune also has faint rings and ring arcs. The rings are made of dust and small particles, much darker and less massive than the bright rings of Saturn. Some parts are clumpy, forming arcs rather than smooth continuous bands. These arcs are influenced by the gravity of nearby moons, especially through resonant effects that help confine the material. The rings occupy a region close to Neptune, but they show the same basic principle seen farther out. Gravity shapes small material into patterns. Even dust cannot simply spread at random when moons and resonances guide its motion. Above and below Neptune's orbital plane, the planet's influence appears in the tilted paths of distant objects, Trojans, and irregular moons. Neptune does not fill that volume with material, but it shapes how material can survive there. Some paths are protected by timing, some are unstable because they approach too closely, some are remnants of capture. The region becomes a gravitational sorting field. Small bodies that enter it may be held, moved, or removed depending on speed, angle, and timing. Neptune's orbital region is strange because it combines calm and disturbance. The planet follows a steady path, yet its gravity has rearranged countless smaller bodies. It protects Pluto-like resonant objects, holds Trojan companions, carries a captured moon, confines faint ring arcs, and scatters icy fragments toward other regions. Above and below the main plane, its influence gives shape to hidden populations that are difficult to see but clear in motion. In this inward step, the solar system becomes more planetary, yet it remains wide and layered, with Neptune acting as a quiet blue anchor in the cold outer dark. Inside Neptune's wider region, the solar system becomes more clearly arranged around the shared plane of the major planets. This plane is not an exact surface, and the planets do not all follow the same perfect line. It is a broad reference shape created by the original rotating disk of gas and dust from which the planets formed. Most of the major planets orbit close to it, and many smaller bodies also keep some relation to it. Yet above and below this plane, hidden populations and tilted paths show that the solar system is not simply flat. The giant planet region, from Neptune inward through Uranus, Saturn, and Jupiter, is a wide gravitational field where the old disk remains visible, but where many objects have been lifted, captured, scattered, or broken away from calmer motion. The plane itself is often described through the ecliptic, which is the plane of Earth's orbit around the Sun, or through the invariable plane, which is based on the total angular momentum of the solar system. Angular momentum is the measure of rotational motion carried by orbiting and spinning bodies. The invariable plane is more physically central because it reflects the combined motion of the planets, especially the giant planets. Jupiter contributes a large part of this total because of its great mass and orbit. In simple terms, the giant planets help define the main balance of the solar system's motion. Their shared plane is a memory of the ancient disk, even after billions of years of gravitational change. Jupiter, Saturn, Uranus, and Neptune do not orbit in exactly the same plane. Each orbit has a small tilt. These tilts are modest compared with many smaller bodies, but they matter because they show that the planetary system is not perfectly level. Over time, the planets pull on one another, and their orbital planes slowly shift. This long-term motion is called secular evolution, meaning gradual gravitational change that does not depend on one single close encounter. The planets remain stable on human timescales, but their orbits breathe slightly in shape and tilt over long periods. The giant planet plane is therefore not a frozen sheet. It is a slowly changing balance among large bodies. Above and below this plane, many irregular moons move around the giant planets. These moons are different from the large regular moons that orbit close to their planets in nearly circular paths near each planet's equator. Irregular moons tend to be small, distant, tilted, and often eccentric. Many are thought to be captured objects, meaning they formed elsewhere and were later held by a planet's gravity. Capture is not simple, because an object passing a planet usually has too much energy to stay. In the early solar system, gas drag, collisions, or three-body interactions may have allowed some bodies to become bound. The result is a collection of small moons moving on strange paths high above and below the local moon planes of the giant planets. Jupiter has many irregular moons, grouped into families that may come from larger captured bodies later broken by impacts. Some orbit in the same direction as Jupiter's rotation, while many orbit in the opposite direction. Saturn, Uranus, and Neptune also have irregular moons with inclined and distant paths. These moons are hidden in plain structure, not hidden because none are known, but hidden because their faintness and complicated motion make the systems around the giant planets much richer than the bright large moons suggest. They show that the giant planets have collected fragments from the outer solar system and kept them in tilted orbits for long spans. The giant planets also hold Trojan populations. Jupiter's Trojans are the largest known group, sharing Jupiter's orbit around the Sun while staying near stable regions ahead of and behind the planet. These bodies do not sit exactly still. They drift around their stable zones in long, looping paths. Many have dark, reddish surfaces, and they may preserve material from the outer solar system, though their exact origins remain studied. Some models link their capture to early migration of the giant planets. They occupy the same general orbital distance as Jupiter, yet many have inclinations that carry them above and below the main plane. Their presence shows that even the path of a planet can contain a thick cloud of small companions. Centaurs also move through the giant planet region. A centaur is a small icy body whose orbit lies among the giant planets and is usually unstable over long times. Centaurs often cross or approach the orbits of one or more giant planets, making them vulnerable to repeated gravitational changes. Some may come from the scattered disk and later become short-period comets. Others may be ejected outward or inward. Their orbits can be tilted, elongated, and temporary. The centaur population forms a moving bridge through the giant planet region, carrying icy bodies across paths where planetary gravity keeps changing their direction. Some centaurs show comet-like activity even far from the Sun. This activity may come from volatile ices that can turn into gas at low temperatures, from crystallization of amorphous water ice, or from other surface processes. Amorphous ice is ice without a regular crystal structure, and when it changes into crystalline ice it can release trapped gases. The details vary by object and remain under study. Activity in this region shows that small bodies do not need to enter the hot inner solar system to begin changing. Even in the cold zone among the giant planets, sunlight and internal processes can disturb ancient ice. The giant planet plane also contains dust and small debris. Dust can come from collisions among small bodies, from active centaurs, from irregular moons, and from impacts on moons and rings. Radiation pressure, solar wind, and planetary gravity slowly alter the paths of these grains. Around each giant planet, rings and faint dust structures form local flat systems, but not all dust remains confined. Some grains move on inclined paths, and some are swept up by moons or planets. The dust is thin. but it records ongoing grinding and erosion in a region that may otherwise appear quiet. The space above and below the giant planet plane is also important for spacecraft exploration. Most spacecraft travel near the ecliptic because reaching the planets efficiently usually means following the main orbital plane. This leaves high-latitude regions less directly sampled. Ulysses, a spacecraft that used Jupiter's gravity to leave the ecliptic, measured the solar wind from high solar latitudes. But the giant planet region itself remains far more explored near the plane than far above or below it. The lack of direct sampling means that many tilted small bodies and dust populations are known through telescope surveys and orbital calculations rather than close inspection. The giant planet region is strange because its broad order contains many hidden exceptions. 4 massive planets define much of the solar system's main plane, but around and among them move objects on paths that rise above and fall below that plane. Captured moons circle at steep angles. Trojan swarms share planetary orbits while spreading vertically. Centaurs wander through unstable routes. Dust and fragments mark collisions and slow erosion. The original disk still shapes the region, but gravity has stirred it into layers. In this inward step, the solar system appears flatter than the distant reservoirs, yet its upper and lower spaces remain filled with tilted histories and quiet motion. Inside the region shaped by the giant planets, the solar system narrows toward the main asteroid belt between Mars and Jupiter. This belt is often imagined as a flat ring of rocks, but it is better understood as a broad zone of small bodies with many different paths. Most asteroids orbit near the main plane of the planets, yet many do not stay exactly within it. Their orbits have inclinations that lift them above and below the ecliptic, forming a thickened region rather than a thin band. The belt is not crowded in the ordinary sense. Its objects are separated by large distances. Still, together they make a rocky population whose vertical structure preserves both ancient formation patterns and long gravitational disturbance. The asteroid belt contains material that never became a planet. In the early solar system, dust and rock gathered into larger bodies called planetesimals, meaning small planetary building blocks. Some joined to form planets, others remained smaller or were broken apart. Between Mars and Jupiter, Jupiter's strong gravity prevented the material from growing into a single large planet. Repeated gravitational tugs raise speeds among small bodies, making collisions more likely to break objects than to join them gently. The modern belt is therefore a remnant field, not the remains of a fully formed planet. Its rocks are survivors of accretion, stirring, impact, and loss. The vertical thickness of the asteroid belt comes from orbital inclination. An asteroid with a low inclination remains close to the ecliptic. An asteroid with a higher inclination travels above that plane for part of its orbit, and below it for another part. Since the belt stretches around the Sun, these tilted paths create a broad three-dimensional swarm. The height reached by each asteroid depends on both its distance from the Sun and its tilt. Even a modest tilt can place an object far from the main plane when measured across millions of kilometers. In this way, the belt becomes a rocky region with hidden height. Not all asteroids share the same composition. Some are dark and carbon-rich, containing minerals altered by water in the early solar system. Others are brighter and richer in silicate rock. Some contain metal, including iron and nickel, likely from the interiors of differentiated bodies that were later broken apart. Differentiated means a body became warm enough for heavier material to sink inward and lighter material to rise, forming layers. When such a body is shattered, fragments can expose material from different depths. The asteroid belt, therefore, contains pieces of many kinds of early bodies, from primitive rock to fragments of once layered worlds. The belt structure is strongly shaped by resonances with Jupiter. A resonance occurs when an asteroid's orbital period forms a repeated ratio with Jupiter's orbital period. In some resonances, repeated gravitational tugs increase an asteroid's eccentricity or inclination until its path changes enough to leave a region less populated. These gaps are known as Kirkwood gaps. They are not empty lines in space that a passing spacecraft would clearly see, but patterns in the distribution of asteroid orbits. Resonances can remove objects over long times, sending some into paths that cross Mars or even approach Earth. The belt's hidden architecture is written in these missing orbital rhythms. Collisions also shape the asteroid belt. When asteroids strike each other, they can chip away fragments, break bodies apart, or form families of related objects. An asteroid family is a group of bodies with similar orbits and often similar compositions, thought to come from a common parent body. Some families spread above and below the plane according to the energy of the original collision and later gravitational changes. Over time, sunlight also affects small asteroids through a subtle process called the Yarkovsky effect. This effect occurs when an asteroid absorbs sunlight and later releases heat, producing a tiny push that can slowly change its orbit. For small bodies over long periods, even such a faint force matters. Some asteroids have unusually high inclinations. They travel far above and below the main belt compared with calmer populations. Their paths may have been stirred by resonances, past encounters, or early rearrangements of the planets. These high-inclination asteroids are important because they show that the belt is dynamically active over long time. It is not merely a storage shelf of rocks. Gravity, collisions, sunlight, and thermal forces keep altering the population. Many changes are slow. But the belt has existed for billions of years, and slow changes become large over that span. Ceres is the largest object in the asteroid belt and is classified as a dwarf planet. It is rounded by its own gravity and contains rock mixed with significant amounts of water-bearing minerals and ice. Observations by the Dawn spacecraft show bright deposits rich in salts on its surface, especially in a Keter crater. These deposits indicate that briny liquid, meaning salty water, may have reached or neared the surface in the relatively recent geological past. Ceres is not only a rock. It is a small world with a complex interior history. Its orbit remains within the belt, but its nature shows that the belt contains bodies with more varied histories than simple fragments. Vesta, another large asteroid studied by Dawn, has a different character. It is rocky and differentiated, with a large impact basin near its south pole. Meteorites found on Earth have been linked to Vesta through their composition and spectra, meaning patterns in reflected light. These meteorites show that fragments from the asteroid belt can reach Earth after being delivered through resonances and planetary encounters. The belt is therefore not isolated. It sends material inward, including pieces that become meteorites. Some of those pieces come from bodies that once had internal heat, crusts, mantles, and deeper layers. Above and below the asteroid belt, there are also objects in related but distinct populations. Some asteroids share Jupiter's orbit as Trojans farther out, while others cross the paths of Mars or Earth farther in. Within the belt itself, inclined orbits create a rocky thickness that connects to these neighboring populations through gravitational pathways. A small change in an asteroid's orbit can place it into a resonance. From there, it may begin a long journey inward or outward. The vertical structure of the belt is therefore linked to motion across the solar system, not only to height above a plane. The asteroid belt is strange because it looks simple from far away and complicated when examined closely. It is a region of rocks, but those rocks are chemically diverse, dynamically stirred, and vertically spread. Some are primitive leftovers, some are pieces of broken layered bodies, some move in quiet paths near the plane, while others climb far above and below it. Jupiter's gravity carves gaps, collisions make families, sunlight nudges small bodies, and dwarf planets keep records of internal change. In this inward step, the solar system's hidden upper and lower spaces are no longer filled mainly with ice. They become a rocky volume of fragments, tilted orbits, and ancient impacts. Inside the asteroid belt, the solar system becomes brighter, warmer, and more crowded with sunlight. This region stretches through the space of Mars, Earth, Venus, and Mercury, where rocky planets orbit close to the Sun and where small grains, fragments, and faint streams of material move through the inner planetary system. It may seem cleaner than the asteroid belt because there is no broad ring of large rocky bodies in the same way, but the space between the inner planets is not empty. It contains dust, meteoroids, small asteroids, cometary debris, and particles shaped by sunlight. Above and below the planetary plane, this material forms a thin, quiet cloud that reveals itself most clearly by the light it scatters. The most visible sign of this inner dust is the zodiacal light. It appears under dark skies as a faint glow along the path of the planets, caused by sunlight reflecting from dust grains spread through the inner solar system. The glow is strongest near the sun's direction because more dust lies along that line of sight, and because the grains scatter sunlight. The dust is concentrated near the plane of the planets, but it is not trapped in a perfectly flat sheet. It has thickness, with grains on inclined paths that rise above and below the ecliptic. From far away, the inner solar system would not look like empty space around the planets. It would contain a broad, faint lens of dust. The grains that make this glow are very small, often comparable to smoke particles or fine powder. Some come from collisions among asteroids. Some come from comets, which release dust as their ices warm and turn into gas. Some may come from older streams of debris that have spread out over time. Once released, the grains do not remain unchanged. Sunlight pushes on them through radiation pressure, and the solar wind also affects them. A process called Poynting-Robertson drag slowly causes many grains to spiral inward toward the sun. This happens because grains absorb sunlight and re-emit energy in a way that removes a little orbital motion over time. The effect is weak, but for tiny particles it is important. As dust moves inward, it may collide with other grains, fall into the sun, or be swept up by planets. The inner dust cloud is therefore constantly renewed. Without new dust from comets and asteroids, much of it would disappear over time. This gives the region a quiet cycle of production and loss. A small asteroid breaks apart, a comet sheds dust, grains drift inward, some burn in planetary atmospheres as meteors, others continue toward the sun. The dust is ancient in origin, but many individual grains have relatively short lives compared with planets. The glow seen in dark skies is a present pattern made from continual small destruction. Meteoroids are larger than dust grains but smaller than asteroids. They move through the inner solar system on many different paths. Some are fragments from asteroid collisions, some are pieces of comets, when a meteoroid enters Earth's atmosphere and heats the air around it. The visible streak is called a meteor. If a piece reaches the ground, it is called a meteorite. These names describe stages of the same material in different settings, in space. The inner solar system contains countless such small fragments, many too faint to track individually. Their orbits can be tilted, stretched, and clustered into streams. Meteor streams form when comets or some active asteroids leave trails of debris along their orbits. Over time, the debris spreads into a long path around the Sun. When Earth crosses such a stream, a meteor shower can occur. The particles appear to come from a particular direction in the sky because Earth moves into the stream along a shared geometry. The stream itself may be inclined relative to the ecliptic, so its material can approach from above or below Earth's orbital plane. This shows that the inner solar system's hidden structure is not only a flat dust lens, but also a set of crossing paths left by older bodies. Near-Earth asteroids are another important population in this inner region. These are asteroids whose orbits bring them near Earth's orbit, though near in astronomy does not always mean dangerous. Many are small and dark. Some come from the asteroid belt after resonances and thermal forces shift their paths inward. Others may be dormant comets, meaning comet-like bodies that have lost most visible activity. Their orbits vary widely. Some stay mostly outside Earth's orbit. Some cross it. Some move inside it for part or all of their paths. The population is constantly changing over long time because planetary encounters can alter orbits, and impacts or solar heating can break small bodies apart. Some small bodies spend most of their time inside Earth's orbit, where observing them is difficult because they appear close to the Sun in the sky. These include objects near Venus's orbit, and rare bodies that move mostly inside Mercury's orbit. Searches for such objects must look near twilight or use spacecraft and survey methods suited to the Sun's glare. The region close to the Sun may contain fewer stable small bodies than farther zones because solar heating, radiation, and planetary perturbations remove or alter them. Still, observations show that the inner solar system has hidden small object populations that are difficult to detect from Earth. Dust also interacts with the rocky planets. Mars has moons and dust-rich space nearby, though its atmosphere and surface dust belong to the planet itself. Earth gathers interplanetary dust every day as tiny particles settle through the atmosphere. The Moon's surface records impacts from micrometeoroids because it has no thick atmosphere to stop them. Venus and Mercury also receive impacts from small bodies and dust. Across the inner region, planets act like moving collectors, sweeping through faint streams of material. Most grains are small enough to vanish without notice, but over geological time their arrival becomes part of surface history. Above and below the inner planetary plane, sunlight becomes the main sculpting force for small material. Gravity still rules the large paths, but radiation pressure can push tiny grains into different orbits. Charged dust can also respond to magnetic fields carried by the solar wind. Near the Sun, heat can change minerals, remove volatile material, and fracture fragile grains. The closer material moves inward, the more strongly it is altered. In this way, the inner solar system is not only a region of rocky planets, it is a bright processing zone where dust and fragments are warmed, pushed, ground down, and absorbed. The inner planet space is strange because it seems open, yet it is filled with fine traces of broken worlds. Its hidden things are not usually large. They are small grains glowing in scattered sunlight, meteor streams crossing planetary paths, dark asteroids moving near the Sun, and dust slowly spiraling inward, above and below the ecliptic. These particles form a faint three-dimensional cloud that changes with collisions, comet activity, and solar forces. In this inward step, the solar system becomes warm and bright, and its hidden material becomes finer, more fragile, and more closely tied to the light of the Sun. Inside the space of the inner planets, the view turns toward the Sun itself, but not yet into its depths. Above and below the Sun, beyond the familiar line of the planets, lie the solar polar regions. These regions are difficult to study from Earth because Earth orbits near the Sun's equatorial plane. Most spacecraft also travel close to that same broad plane, following paths shaped by planetary motion and launch energy. As a result, the Sun's north and south poles are less directly observed than its equatorial regions. They are not hidden by darkness, but by viewpoint. The poles face away from the usual path of observation, making them quiet frontiers in the study of the nearest star. The Sun is a rotating ball of hot plasma. Plasma is gas so hot or energized that many atoms have lost electrons, allowing charged particles to move freely. The Sun does not rotate like a solid body. Its equator turns faster than its higher latitudes, and the poles rotate more slowly. This uneven rotation helps twist and reshape the Sun's magnetic field. The magnetic field is central to solar activity because it guides charged particles, stores energy, and produces features such as sunspots, loops, eruptions, and the solar wind. Near the poles, the magnetic field often has a simpler large-scale pattern during quieter parts of the solar cycle, though it changes strongly over time. The solar cycle lasts about 11 years from one activity maximum to the next. During this cycle, the Sun's magnetic field changes in strength and structure. Sunspots become more numerous near maximum and fewer near minimum. The global magnetic field also reverses, so the north and south magnetic polarities switch places. The polar regions are important because their magnetic fields help set the conditions for the next cycle. Measurements of polar magnetism are therefore a way to understand the Sun's long rhythm. Observations indicate that the strength of the polar fields near minimum is linked with the strength of the following cycle, though the details of prediction remain uncertain. At the Sun's poles, large dark regions called coronal holes often appear during quieter times. A coronal hole is not an actual hole in the Sun. It is an area in the outer solar atmosphere where the plasma is cooler and less dense than nearby regions, making it darker in certain ultraviolet and X-ray wavelengths. The magnetic field in a coronal hole is more open, meaning field lines extend outward into space instead of closing back to the Sun nearby. These open fields allow solar wind particles to escape more easily. Polar coronal holes can therefore be sources of fast solar wind flowing outward from high latitudes. Fast solar wind from polar regions was measured directly by the Ulysses spacecraft. Ulysses used Jupiter's gravity to enter a path that carried it above and below the Sun's poles. It found that during solar minimum, fast wind flowed from high latitudes, while slower, more variable wind was more common near the solar equator. This pattern changed near solar maximum, when the magnetic field became more complex and the distinction between high and low latitudes weakened. These measurements showed that the Sun's polar regions are not just remote viewpoints. They are sources of major streams that help fill the heliosphere. The polar solar wind matters because it shapes the three-dimensional space around the Sun. The planets move mostly near the equatorial region, so many measurements sample that zone. High-latitude solar wind shows that the heliosphere has structure above and below the planetary plane. It carries magnetic fields, charged particles, and waves outward into space. Its speed, density, and temperature differ from equatorial wind depending on the solar cycle. This means that the Sun does not breathe evenly in all directions. It releases material into space in patterns tied to latitude, magnetism, and time. The Sun's polar regions also contain flows on the surface and beneath it. Plasma moves slowly from lower latitudes toward the poles in a circulation pattern called meridional flow. This flow helps transport magnetic flux, meaning magnetic field strength spread across an area, from active regions toward the poles. There, magnetic fields can accumulate, weaken, reverse, and rebuild through the cycle. These motions are slow compared with eruptions, but they help govern the long-term magnetic pattern. The visible surface is only the outer sign of deeper movement, yet even surface measurements show that the polar regions are part of a global circulation system. Studying the poles is difficult because of foreshortening from Earth's viewpoint. Foreshortening means that features near the visible edge of the sun appear compressed and harder to measure. Since the poles are usually seen at an angle, magnetic measurements there are less precise than those near the center of the solar disk. The sun's axis is tilted slightly relative to Earth's orbit, so each pole becomes a little more visible during part of the year, but the view remains limited. Spacecraft placed away from the ecliptic can improve this view, though such missions require special trajectories and careful planning. The European Space Agency and NASA Mission Solar Orbiter is helping improve understanding of the Sun from higher latitudes. It does not pass directly over the poles in a simple vertical path, but its orbit gradually tilts so it can view the Sun from angles not available near Earth. Its instruments study the solar wind, magnetic fields, particles, and images of the Sun's surface and atmosphere. These observations are important because the polar magnetic field, polar coronal holes, and high-latitude flows all connect to the larger solar cycle. More complete views help turn the Sun from a mostly equatorial object of study into a three-dimensional star. Above and below the Sun, there are no solid polar caps like those on a planet. There is no frozen surface and no ground. The poles are regions of latitude on a luminous plasmasphere. Their hidden nature comes from the way magnetism and viewpoint combine. The polar atmosphere opens into space through coronal holes. The magnetic field changes polarity with the cycle. Fast wind streams outward along open field lines. Slow flows carry magnetic patterns across the surface. The region appears quiet compared with bright active areas, but it plays a central role in the Sun's long magnetic behavior. The solar polar regions are strange because they are part of the nearest star and still remain partly difficult to see. They shape the heliosphere from above and below, yet most observation has long come from near the planetary plane. Their magnetic fields reverse, their coronal holes breathe with the cycle, and their fast wind reaches outward into space. In this inward step, the hidden things above and below the solar system become directly solar. They are not distant icy bodies or tilted rocks, but fields and flows on a star, opening from the poles into the surrounding darkness. Beneath the visible face of the Sun lies a layered interior where light is made, delayed, reshaped, and finally released. The Sun has no solid surface in the ordinary sense, but it has regions defined by temperature, density, pressure, and the way energy moves. The visible surface, called the photosphere, is the layer from which most sunlight escapes into space. Above it are the chromosphere and corona, parts of the solar atmosphere. Below it, the Sun becomes opaque, meaning light cannot travel freely for long distances. Photons, the particles of light, are absorbed and re-emitted many times. In this inward region, the Sun's bright, calm appearance gives way to hidden motion inside hot plasma. Just below the photosphere is the convection zone. Convection is the movement of warm material rising and cooler material sinking. In the Sun, this material is plasma rather than liquid water or air. But the basic idea is similar. Energy carried outward from deeper layers makes plasma less dense, so it rises. Nearer the surface, it cools and sinks again. This motion forms patterns on the photosphere called granulation, where bright cells show rising hot plasma and darker edges show cooler sinking plasma. Each visible grain is a sign of deeper motion, a surface pattern made by heat escaping through moving matter. The convection zone extends inward for a large part of the Sun's radius. It is turbulent, meaning its motions are irregular and full of swirling changes. This turbulence helps shape the Sun's magnetic field. Because plasma carries electric charges, its movement can generate and stretch magnetic fields. The Sun's uneven rotation works with convection to drive a magnetic dynamo, a process that maintains and changes the global magnetic field. The dynamo is not seen directly as a machine. It is inferred from solar rotation, plasma flow, magnetic cycles, and mathematical models. Its exact details remain under study, but it is central to the Sun's activity. At the lower edge of the convection zone lies a transition region called the tachocline. This is where the Sun's outer layers, which rotate at different speeds by latitude, meet deeper layers that rotate more uniformly. The sharp change in rotation may help organize and strengthen magnetic fields. The tachocline is hidden far below the surface, but it is important in many models of the solar cycle. It may store or stretch magnetic fields before they rise toward the surface as active regions. These rising fields can form sunspots, where strong magnetism suppresses convection and makes parts of the surface appear darker. Below the tachocline is the radiative zone. In this region, energy moves mainly by radiation rather than by large-scale rising and sinking motions. Photons do not fly straight outward from the core to the surface. The plasma is dense, and light interacts with particles again and again. A photon may travel only a short distance before being absorbed and re-emitted in a new direction. The outward journey of energy is therefore extremely slow compared with the speed of light in open space. Energy made deep inside can take a very long time to reach the surface, passing through countless interactions before becoming the sunlight that leaves the Sun. The radiative zone is stable against strong convection because the temperature and density change in a way that allows radiation to carry energy efficiently enough. The plasma is still hot and dense, but it does not churn like the convection zone above it. Its hidden motion is more subtle, governed by radiation, pressure, and slow internal rotation. This region makes up much of the Sun's interior volume. It acts as a thick glowing barrier between the core and the turbulent outer layers, delaying and smoothing the energy flow that began deeper down. Scientists study the Sun's interior through heliosismology. Heliosismology is the study of waves moving through the Sun. The Sun rings with many kinds of pressure waves, produced by turbulent motion near the surface. These waves travel through the interior and return to the surface, where their patterns can be measured. By studying them, scientists infer internal temperature, density, flow, and rotation. This is similar in principle to using seismic waves to study Earth's interior, though the Sun is made of plasma rather than rock. Helioseismology shows that the Sun is not a simple glowing ball. It has hidden layers with measurable structure. The Sun's interior is held in balance by gravity and pressure. Gravity pulls all material inward. Pressure pushes outward. This balance is called hydrostatic equilibrium. If inward gravity became stronger than pressure, the Sun would contract. If outward pressure became stronger than gravity, it would expand. In the present Sun, these forces remain closely balanced. The pressure comes from hot particles and radiation inside the Sun. The deeper the layer, the greater the weight of material above it, and the higher the pressure and temperature must be. This balance allows the Sun to remain stable over very long spans of time. The material inside the Sun is mostly hydrogen and helium. Hydrogen is the lightest element, and helium is the next lightest. Heavier elements make up only a small fraction by mass, but they matter because they affect opacity, or how easily radiation passes through plasma. Small differences in the abundance of heavier elements can influence models of the solar interior. Measurements of the Sun's surface composition, combined with heliosismology, have led to careful comparisons and some remaining tensions in solar models. Observations support the broad picture of the Sun's layered structure, while details of composition and opacity remain active areas of research. Energy does not move through the Sun in a single simple form. In the deepest layers it begins from nuclear reactions. In the radiative zone it moves through repeated absorption and emission of radiation. In the convection zone it is carried by moving plasma. Near the surface it escapes as light. Each region changes the way energy travels without creating a sharp, solid boundary. These layers are defined by physical behavior, not by walls. The Sun's hidden interior is therefore a set of transitions in movement, pressure, and transport. The solar interior is strange because it is the source of ordinary daylight, yet it cannot be seen directly. The calm light that reaches planets begins beneath layers that trap, scatter, churn, and release energy over immense time. Above and below the solar surface, magnetic fields open into space, but inward from that surface the star becomes denser, hotter, and more opaque. The convection zone rolls with plasma. The tachocline marks a hidden change in rotation, and the radiative zone carries energy through a slow maze of light and matter. In this inward step, the hidden regions are no longer distant from the Sun. They are inside it, beneath the bright surface that makes the solar system visible. At the deepest level of the Sun lies the core, a region where matter is compressed to extreme density and temperature, and where the energy that supports the entire solar system is created. The core occupies the central portion of the Sun, extending outward from the very center to a fraction of the solar radius. It is not visible in any direct sense. No light escapes from it without first passing through the dense layers above. Its presence is known through physics. Observation of the Sun's total energy output, neutrino measurements, and models tested against heliosismology. In this hidden region, the quiet process of nuclear fusion transforms mass into energy. The temperature in the core reaches many millions of degrees Celsius. At such temperatures, matter exists as plasma, with atomic nuclei and electrons moving freely. The pressure is enormous because of the weight of all the layers above pressing inward. Under these conditions, hydrogen nuclei, which are single protons, can come close enough to overcome their natural electrical repulsion. When they do, they can fuse to form helium through a series of reactions known as the proton-proton chain. This chain does not occur in a single step. It involves intermediate particles and reactions, gradually converting 4 hydrogen nuclei into 1 helium nucleus. In the process of fusion, a small amount of mass is lost. This mass does not disappear. It is converted into energy according to the relation between mass and energy, described by modern physics. That energy emerges in the form of high-energy photons and other particles. The total energy released in the core supports the Sun against gravitational collapse and provides the light and heat that reach the planets. Without continuous fusion in the core, the Sun would not remain stable over long time. The core is therefore the quiet engine of the solar system. One of the byproducts of fusion in the core is the neutrino. A neutrino is a very light, nearly massless particle that interacts only weakly with matter. Because of this, neutrinos produced in the core can pass through the Sun's layers and escape into space almost without delay. They travel in straight paths at nearly the speed of light, On Earth, detectors deep underground or under ice can measure some of these particles. Observations of solar neutrinos confirm that fusion is taking place in the Sun's core. Early measurements detected fewer neutrinos than expected, which led to further study. It was later understood that neutrinos can change type during travel, explaining the difference between prediction and detection. The photons produced in the core do not escape so quickly. They begin with high energy, but as they move outward through the dense plasma of the radiative zone, they are repeatedly absorbed and re-emitted. Each interaction changes their direction and energy. The path becomes a long, random walk rather than a straight line. Over time, the energy moves outward, gradually shifting to lower energy photons. By the time it reaches the photosphere, the radiation has become the visible and infrared light that leaves the Sun. The journey from the core to the surface is therefore extremely slow compared with the speed of light in empty space. The balance within the core is delicate but stable. Gravity pulls inward, trying to compress the Sun further. The pressure from hot particles and radiation pushes outward. Fusion in the core maintains the temperature needed to keep this pressure high enough. If the core were to cool slightly, pressure would drop, gravity would compress the core, and the temperature would rise again, increasing fusion rates. If the core were to heat too much, pressure would increase, causing the core to expand and cool, reducing fusion. This feedback maintains a steady state known as hydrostatic equilibrium combined with thermal balance. The composition of the core changes slowly over time. As hydrogen is fused into helium, the proportion of helium increases. Helium nuclei are heavier than hydrogen nuclei, so the average mass of particles in the core increases. This affects pressure and temperature. Over billions of years, the Sun's core gradually becomes richer in helium, and its energy production changes slowly. The Sun is currently in a stable phase where hydrogen fusion dominates. This phase is expected to last for several billion more years before deeper changes occur. The long stability of the core allows life on Earth to exist over extended spans. The core's conditions cannot be reproduced directly on Earth at the same scale, but nuclear physics experiments and models describe the reactions involved. The rates of fusion depend on temperature, density, and the probability of particles overcoming repulsion. Small changes in these conditions can alter energy production. Observations of the Sun's brightness and neutrino output place strong limits on how the core behaves. These measurements show that the Sun is stable to a high degree, with only small variations in total output over time. The core does not flare or pulse in the way the surface sometimes does. Its changes are slow and steady. Above and below the solar system, in the larger sense, everything depends on this central region. The light that fills interplanetary space, the solar wind that shapes the heliosphere, the warmth that allows planets to have atmospheres and oceans, all begin with reactions in the core. The polar regions, the dust clouds, the asteroid fragments, and the distant icy bodies all exist within a system powered by this hidden source. The core does not extend upward or downward in a directional way, because it is the center, yet it connects to every direction equally through the energy it produces. The core is strange because it is both remote and immediate. It lies far beneath layers of plasma that no instrument can penetrate directly, yet its effects are present in every ray of sunlight. It is a place of intense heat and pressure, yet it operates through simple reactions repeated countless times. It converts mass into energy quietly, without sound, without sudden change on human timescales. It holds the Sun in balance and sustains the wider system. In reaching this innermost region, the path from the galactic halo to the solar core becomes complete. moving from faint outer structures to the dense center where energy is born. The solar system rests within many layers, from the faint outer reach of the galaxy to the quiet center of the sun. Above and below its familiar plane, space is not empty. It holds ancient stars, thin gas, magnetic fields, icy reservoirs, tilted worlds, scattered rocks, drifting dust, and streams of charged particles. Each region has its own scale and its own kind of stillness. Some are wide enough to be shaped by the Milky Way. Some are small enough to glow as fine grains in sunlight. Some are hidden by distance, and some are hidden by the limits of viewpoint. The path inward shows a system that is not only a flat arrangement of planets, it is a layered structure shaped by gravity, pressure, light, ice, rock, plasma, and time. The far cloud of comets surrounds the sun from all directions. The Kuiper belt and scattered disk preserve cold remnants from early formation. Neptune and the giant planets guide small bodies into rhythms and tilted paths. The asteroid belt carries broken records of rocky beginnings. The inner solar system gathers dust and faint debris into a soft glow. The sun's poles open into space with magnetic fields and wind. Beneath the surface, hidden layers carry energy inward to outward, until the core remains as the calm source of light. Nothing in this path requires a sharp edge or sudden ending. Each region changes gradually into another. The solar system becomes a set of borders that breathe, reservoirs that wait, and motions that continue. In the dark above and below, the hidden things remain quiet, not separate from the known planets, but part of the same long structure around a star.